This is rates FRQ number 2 from the 2018 exam. The mean score is a 2.82. And in this question, I am given a rate at which people are entering an escalator. And I know it's a rate because it tells me, and also because my units are people per second, which is a rate unit. And I'm also given information about the rate at which they exit the escalator. So they're going to exit at a constant rate of 0.7 people per second. They didn't explicitly define a function, so what I like to do is define my own function as that constant function, which is 0.7. It also tells me there's 20 people to begin with at t equals 0. Part A says how many people enter the line for the escalator on the time interval from 0 to 300. This is concerned with just the number of people entering the line, so I'm just concerned with R of t on this one. It's helpful to remember the progression of things. It goes people per hour squared. To move downward in this list, you do a derivative, and to move upward in this list, we do an integral. Where we're starting with our given information is at this unit right here, people per hour. So if I want to get up to the number of people, which is what part A is asking me, that tells me I need to integrate. So I do the integral from 0 to 300 of R of t. Don't take your time rewriting this function here. It has a name, so just use its name. When you put that in your calculator, you get 270. So you get a point for the integral, and you get a point for the answer of 270. Part B is asking how many people are in line at t equals 300. I need to consider three things. The number of people that are there initially, which is given up in the stem of the problem, is 20. And then I need to add the number of people that are entering the escalator. I'm going to use that entering rate from 0 to 300, R of t dt. If you just pulled your answer from part A here, because I already actually evaluated that, and if you just pulled the 270 down here, that would be totally okay. And I also need to take into account how many people are exiting the escalator. So I need to subtract 0 to 300 of this newly created function up here that I called E of t. If you didn't do that, you could just think about this from a logical standpoint, and you could say, well, that's just going to be 300 is our time, and then 0.7 per second. So you multiply that, and that'll give you the total number of people. So if you define a function, you could integrate that function, or you could just write the 0.7 in that position right there. Or you could just kind of use common sense and write this 300 times 0.7. Either way, you're going to get an answer of 80 for this. Point-wise, you'll get a point to either write the integral as I have it written here. You could put a 0.7 in place of that e, or you could just do 300 times 0.7, and then you get 1 point for that answer of 80. In part C, we're asked, what is the first time t that there are no people in line for the escalator? And what we're told in a previous part of the problem is for t less than 300, there's always people in line. So it's going to be some time after 300 seconds. And at 300 seconds, I found in part B that there's 80 people in line. So I need to find out how long it's going to take for those 80 people to exit the line. So I'm looking for 0.7 as my rate times whatever that time is. That's what I'm looking for to get to these 80 people. If I divide both sides by 0.7, that's going to tell me what that time is. And I just add that to that initial time of 300. And that will give me this answer of 414.286 or 285. And that answer itself is just worth a point. And our last part wants to know on the interval from 0 to 300. And this is a closed interval, which gives me a clue that I'm going to do a candidates test because I'm looking for a minimum. So I go through that process. I'm looking for endpoints and critical points, and those belong in my candidates table. For my critical points, I just take my rates because they are the derivative. My entering rate minus my exiting rate to equal 0. And that ends up, my exiting rate is the 0.7. So bottom line, I'm looking for where R of t equals 0.7. On the calculator, we're going to be looking for that intersection point. Make sure you know how to use the calculator to find that intersection point. So what I'm going to do on my calculator is set my window to reflect 0 to 300. So your x min is 0 and your x max is 300. And then you're going to want to hit zoom 0 or zoom A And that's going to set your y's to a good setting to find that intersection point. What we're going to find is they intersect in two places, 33.013, and I'm going to go ahead and store that into a variable I'm going to call a because I need to use it later on. And my second intersection point is this 166.574 or 575. I'm going to store that into a variable that I'm going to call b. Point-wise, what you're going to get is a point for one of these setups here. Any of these three, showing us how we're going to find that critical point, is worth 1 point. And to actually come up with this one critical point, the 33.013, is going to earn a second point in part D. And now I set up my candidates table with my 2 critical points and my endpoints of 0 and 300. What determines which of these is the absolute minimum is the number of people in line at each of these times. So I take those times one at a time and I plug them into this equation here, and that tells me the number of people that are in line. So here's my initial amount, plus this will be my number that are entering the line minus the number that are leaving the line. And I come up with these numbers. If I'm looking for my absolute minimum, it's the smallest one, which is occurring here at A. And then I just declare that as my answer. For the remaining 2 points, what you need for this point is to make some sort of a global argument. So you want to have your candidates test set up, or at least show that you're considering these candidates and their amounts of the number of people in line. And this last point is to correctly identify this as the correct answer. And keep in mind that this wanted me to give the answer to the nearest whole number, which is why I wrote 4 here.